You've got the app open on your phone, the little timer counting up, and somewhere around hour 14 or 15 you start glancing at it more often than you'd like to admit. Hour 16 hits and you feel a small flicker of pride. That's the number everyone talks about. But you keep going, and somewhere past that, hunger fades into something quieter, almost like your body stopped asking. You've heard there's a specific hour where something inside you genuinely switches on, some cellular process that isn't running at all until that exact point and then suddenly is. I'm not going to tell you that hour is a magic number identical for every single person reading a fasting app on their phone, because it isn't, and I want to be honest with you about that from the very start. But the switch itself is real. It is one of the most significant discoveries in modern cell biology, and understanding what it actually is, rather than just the popularized hour number attached to it, is going to change how you think about fasting altogether. Before I explain what actually happens at the point where your body genuinely does change how it operates, I want to walk you through the real discovery behind this claim, because the actual science is more interesting and more useful to you than a single dramatic hour count ever could be. The discovery nobody explains properly in 2016, a Japanese cell biologist named Yoshinori Ohsumi won the Nobel Prize in Physiology or Medicine for work he'd spent decades building, uncovering the precise genetic machinery behind a process called autophagy, a word that literally translates to self-eating. Autophagy isn't a fringe concept or a wellness buzzword invented for supplement marketing. It's a fundamental, universal cellular process, present in essentially every cell in every organism from yeast to humans, responsible for identifying damaged proteins, worn-out cellular components, and malfunctioning organelles, wrapping them in a membrane, and delivering them to a structure called a lysosome to be broken down and recycled into raw materials the cell can use again. Ohsumi's research, working initially in yeast because the cellular machinery is easier to observe and manipulate, identified the specific genes responsible for executing this process, work that opened the door to understanding how the exact same system operates inside human cells. Here's the part that connects directly to fasting, and it's genuine, well-established biochemistry. Autophagy isn't running at a constant, fixed rate all the time. It's actively regulated by two opposing molecular systems that function almost like a dimmer switch tied directly to your nutritional state. One of those systems, a protein complex called mTOR, gets activated when nutrients, particularly glucose and certain amino acids, along with the hormone insulin, are abundant in your bloodstream, and when mTOR is active, it actively suppresses autophagy, essentially telling your cells that building and growing is the priority right now, not recycling. The other system, an energy-sensing enzyme called AMPK, gets activated under the opposite condition, when cellular energy is running lower and glucose availability drops, and AMPK does the reverse of mTOR, actively promoting autophagy while suppressing the growth-focused processes mTOR was running. Fasting, by definition, drops circulating glucose and insulin over time, which shifts that balance, quieting mTOR and activating AMPK. And that shift is the actual molecular switch behind everything the popular fasting content is trying to describe with a single dramatic hour number. Now here's where I need to be honest with you about the number itself, because this is exactly the kind of detail that gets flattened into a much more precise-sounding claim than the actual research supports. Directly measuring autophagy in a living human being is genuinely difficult. It typically requires tissue biopsies and specialized lab assays looking for specific molecular markers, which isn't something researchers can easily do repeatedly, hour by hour, across large groups of fasting volunteers. A meaningful share of the specific hour number circulating in popular fasting content, including the number in this video's own title, comes from extrapolating findings out of animal studies, largely in mice, whose metabolism runs considerably faster than a human's, scaled down into a rough human estimate rather than measured directly in humans at that precision. The honest version of this story is that autophagy activation during fasting is real, well documented, and tied to a genuine metabolic threshold, but that threshold is a range that shifts based on your own body, not a fixed universal hour stamped identically onto everyone holding a phone with a fasting timer running on it. It's worth understanding why the mouse research, even with its limitations for pinning down an exact human hour, is still genuinely useful rather than irrelevant. Researchers studying fasting-induced autophagy in mice have been able to do something far harder to ethically or practically replicate in humans, directly sampling tissue at multiple points across a fast and tracking specific molecular markers of autophagosome formation as they rise. That work confirmed, unambiguously, that autophagy does ramp up in response to fasting, that the ramp-up tracks closely with falling insulin and rising glycogen, and that the magnitude of the increase can be substantial. What it can't tell you with precision is the exact human hour equivalent, because converting a mouse metabolic timeline into a human one involves scaling assumptions that researchers themselves treat as rough estimates rather than fixed conversions. A small number of human studies using indirect markers, tracking things like circulating amino acid patterns consistent with protein breakdown and recycling, or LC3 protein conversion in accessible tissue samples from volunteers undergoing supervised extended fasts, have found patterns broadly consistent with rising autophagy over the course of a day-long fast, which is reassuring. But the sample sizes in this kind of human research tend to be small, and the individual variation between participants tends to be large, which is exactly why a single confident hour number was always an oversimplification of what the underlying human data actually shows. It's not a clock. It's a threshold, and the threshold moves. Here's the reframe that actually matters, and it's more useful to you than pretending a single hour number applies identically to every person watching this. What flips that molecular dimmer switch from the mTOR side toward the AMPK side isn't time passing on a clock at all. It's your circulating glucose and insulin dropping low enough, alongside a related and closely tracked depletion of your liver's stored glycogen, the readily available form of stored carbohydrate your liver keeps on hand specifically to buffer blood sugar between meals. Hour 18 works reasonably well as a popularized shorthand because, for a moderately active adult eating a fairly typical mixed diet, that's roughly when average liver glycogen stores tend to run low enough to meaningfully shift that hormonal balance. But roughly and average are doing real work in that sentence, and the actual threshold for any individual person depends heavily on factors that number completely ignores. Let's walk through the mechanics of this threshold properly, because once you understand what's actually being measured, the variation between people stops being confusing and starts making complete sense. Think of your liver's glycogen stores like a small emergency generator sitting in reserve, ready to keep your blood sugar steady the moment you stop eating. That generator holds a genuinely limited amount of fuel, roughly somewhere in the neighborhood of 80 to 120 grams of stored glycogen in an average adult liver, though that number itself varies with body size and recent dietary habits. Every hour you go without eating, your liver taps that generator to keep blood glucose from dropping too low, and the moment that reserve runs meaningfully low, your body has to shift its primary fuel strategy, relying increasingly on breaking down fat for energy instead. A transition that also involves rising levels of circulating ketones as your liver starts converting fat into an alternative fuel source your brain and other tissues can run on. That broader shift, sometimes called the metabolic switch in the research literature, tracks closely alongside the mTOR to AMPK shift discussed above, because both are downstream of the same underlying event, your glucose and insulin availability dropping low enough that your body's overall priority genuinely changes from processing incoming fuel to managing a limited internal reserve. The size of the glycogen generator, and how quickly you drain it, is not the same for every person walking around with a fasting app on their phone, which is exactly why a single universal hour number was always going to be an oversimplification. There's a second layer to this threshold worth understanding, because it explains why the shift feels gradual rather than sudden even once it does begin. As glycogen runs low and insulin drops, a second hormone, glucagon, insulin's counterpart, rises to help mobilize stored fat and support the liver's shift toward producing ketones. That insulin to glucagon crossover doesn't happen as a single discrete moment either, it unfolds gradually over a period of hours, which means the mTOR to AMPK shift driving autophagy is riding on top of a hormonal transition that was itself never designed to flip instantly. This is part of why some researchers studying this process describe it less like a switch being thrown and more like a dial slowly being turned, which is a far more accurate mental model than a single hour number ever could be, even though the dial that gradually turns somewhere in a range depending on your glycogen and hormones was never going to make for as clean a headline as a specific number. Why the switch flips earlier for some people and later for others, this isn't randomness, and it isn't a flaw in the science. There are a small number of specific, well-understood factors that shift exactly when this threshold gets crossed, and once you see them laid out, you'll understand why your own fasting experience might genuinely differ from a number you saw in a video or an app. The first is what you ate before the fast began. Someone who ate a large, carbohydrate-heavy meal the night before starting a fast walks into that fast with a fuller glycogen generator than someone who was already eating lower carbohydrate or had a smaller final meal, and a fuller starting reserve simply takes longer to drain down to the threshold where the hormonal shift kicks in. This alone can shift the practical timing of that switch by several hours in either direction for otherwise similar people. The second is activity level during the fast itself. Physical activity, particularly anything demanding on your muscles, draws down glycogen faster, both liver glycogen supporting blood sugar and the separate glycogen stored directly in muscle tissue. Someone doing a normal amount of walking and daily movement during a fasting window depletes that reserve meaningfully faster than someone sitting still for the same stretch of hours, which is part of why some research and a fair amount of practical reporting from people who fast regularly suggests that combining a fasting window with light to moderate exercise can shift the metabolic switch earlier than fasting alone would. The third, and this one connects directly to why this topic fits a channel focused on the specific challenges of getting older, is age itself, and it cuts in a genuinely important direction. Autophagy efficiency isn't just about when the switch flips. Research on aging cell biology has repeatedly identified declining autophagic capacity as one of the recognized hallmarks of the aging process itself, meaning the machinery responsible for actually executing autophagy once that molecular signal arrives tends to become somewhat less efficient with age, independent of whether the signal to activate it shows up on schedule. That's a genuinely different problem than the timing question, and it's arguably more important. Even if an older adult's mTOR to AMPK shift happens at roughly the expected point in a fast, the downstream cellular recycling machinery answering that signal may be running at reduced capacity compared to a younger person's, which is part of why some researchers studying autophagy and aging have specifically highlighted fasting and other autophagy-promoting interventions as potentially more relevant, not less, for adults past midlife, even though the underlying machinery they're trying to activate has itself become somewhat less responsive with age. Why this actually matters beyond a number on an app. One want to walk through the real chain of consequences here honestly, because the reason this specific cellular process draws so much serious research attention has nothing to do with a hunger milestone and everything to do with what autophagy actually does inside a cell over the long run. Cells accumulate damaged, misfolded proteins and malfunctioning organelles as an ordinary, unavoidable consequence of simply operating over time, the cellular equivalent of wear and tear. Autophagy is one of the primary systems responsible for clearing that accumulated damage before it builds up to problematic levels. Research connecting autophagy to neurodegenerative disease has found that several conditions involving abnormal protein accumulation in the brain, including research specifically looking at Alzheimer's and Parkinson's disease, show impaired or insufficient autophagic clearance as part of the underlying disease process, with misfolded or aggregated proteins building up in a way a properly functioning autophagy system would ordinarily have cleared out. This doesn't mean fasting prevents these diseases, that specific causal claim isn't established, but it does mean the clearance system fasting helps activate is the same system researchers have identified as impaired in these conditions, which is a large part of why autophagy has become such a serious, heavily funded area of research well beyond the fasting community online. There's also a genuine quality control role autophagy plays at the cellular level more broadly, helping identify and remove damaged mitochondria specifically, through a related, more targeted version of the same process called mitophagy, replacing them with functional ones rather than allowing a growing population of underperforming, potentially harmful mitochondria to accumulate inside a cell over time. Given how much this channel has already talked about mitochondrial function and cellular energy production, this connects directly. A properly functioning autophagy and mitophagy system is one of the actual, legitimate ways your body maintains mitochondrial quality over the years, distinct from and considerably better established than some of the more exaggerated claims circulating about individual dietary fats. Researchers studying aging biology broadly have increasingly treated autophagy as one of several interconnected systems, alongside things like DNA repair capacity and inflammatory regulation, that together account for a meaningful share of why some people's tissues seem to hold up better over the decades than others facing similar chronological age. None of these systems work in isolation, and autophagy alone isn't a complete explanation for healthy aging any more than any single mechanism discussed on this channel ever is. But it's a genuinely legitimate piece of that larger picture, backed by a body of cell biology research substantial enough to have earned its discoverer a Nobel Prize, which puts it in a meaningfully different category of evidence than many of the more speculative claims currently circulating in popular fasting and longevity content. What actually triggers this properly? Here's where I want to be direct with you, the same way I've been through this entire video. You don't need to chase a specific hour number with obsessive precision to benefit from this system, and doing so can create an unhelpful, anxious relationship with a fasting window that's supposed to be a reasonably simple tool. Extending your typical eating window into a meaningfully longer fasting stretch, generally somewhere in the range of 14 to 18 hours for most moderately active adults eating a typical diet, is enough to produce the hormonal shift discussed above for the majority of people, even if the precise moment it happens varies somewhat from the popularized number. If your goal is specifically supporting this process rather than chasing an exact hour, consistency across most days of the week matters considerably more than perfectly hitting one specific number on any individual day. If you want to shift that threshold earlier without extending the fast itself, reducing carbohydrate intake at your final meal before the fast begins, and including a reasonable amount of movement during the fasting window itself, both work directly on the actual mechanism, a smaller starting glycogen reserve and faster glycogen depletion, rather than trying to force a fixed clock to move. And if you're specifically motivated by the aging and autophagy efficiency angle discussed earlier, it's worth knowing that resistance training and regular physical activity independently support healthy autophagic function as well, meaning the fasting piece works best as one part of a broader picture rather than the single lever responsible for the entire outcome. The myth worth killing here: you've probably seen the confident claim that autophagy simply doesn't happen at all unless you cross a specific, precise hour threshold, 16, or 18, or 24 depending on which video you watched, and that falling short of that exact number means you got none of the benefit. That framing isn't how a hormonally regulated biological threshold actually works. mTOR and AMPK aren't a light switch with only fully on and fully off positions, flipping at one precise instant. They function more like a dimmer, gradually shifting balance as glucose and insulin decline, meaning some meaningful movement toward increased autophagy plausibly begins well before any specific popularized hour number, continuing to build the longer.Fast continues, rather than sitting at zero until one dramatic instant and then suddenly maxing out. The equally common myth running in the opposite direction, that you need multi-day extended fasts to get any meaningful benefit at all, and that ordinary time-restricted eating is essentially pointless, also overstates the case in the other direction, given that the hormonal shift underlying this process genuinely does begin building well within a single day for most people, long before a multi-day fast becomes necessary. Being honest about the limits here, I don't want to oversell this, because doing so would undercut everything true I've said so far. Autophagy is real, well-documented, and genuinely activated by fasting through legitimate, well-understood mechanisms, but the specific claims about exact human timing are considerably less precise than a single confident hour number implies, and it's worth holding that number loosely rather than treating it as a scientific fact carved in stone. Extended and multi-day fasting protocols carry real risks for certain people, including anyone with a history of disordered eating, anyone who is pregnant or breastfeeding, anyone managing diabetes with insulin or other blood sugar medications, and anyone with a chronic medical condition that affects how their body handles extended periods without food. Refeeding after a genuinely prolonged fast, several days or longer, carries its own documented medical risks and generally shouldn't be attempted without medical guidance. This video is describing ordinary time-restricted eating windows within a single day, not an endorsement of extreme or extended fasting protocols undertaken without appropriate supervision. Coming back to that timer on your phone, think back to that moment glancing at the fasting app, watching the number climb past 16, past 18, wondering whether some specific instant just quietly happened inside you. It was never really about that one precise hour flipping a switch identically for every person holding a phone. It's a genuine, Nobel Prize-winning discovery about how cells recycle their own damaged components, regulated by a hormonal balance that shifts gradually as your glycogen reserve drains down, at a pace that depends on what you ate, how much you moved, and, if you're past midlife, on cellular machinery that may be running that recycling process somewhat less efficiently than it used to, regardless of exactly when the signal to start arrives. Picture what's actually useful on the other side of understanding this properly. It isn't anxiously watching a clock for one dramatic number. It's building a consistent, sustainable eating window that reliably gives your body the chance to shift into that recycling mode on a regular basis, paired with the movement and strength training that support the actual cellular machinery carrying that process out, rather than obsessing over whether you personally crossed some universal threshold at exactly the hour a video told you to expect it. The switch was never a single dramatic instant build for a thumbnail. It's a real, gradually shifting balance your body has been running your entire life, responding to how you eat and move, doing exactly what it was built to do the moment you actually give it the chance. Now you know what that switch really is, and exactly what it's waiting on from you, rather than which hour it's supposedly waiting on the clock.